So we're looking at the alcohol and carboxylic acid functional groups here. Before we go on to that, let's just go back a couple of pages, because when we did condensation polymerization, we introduced these homologous series. So this was page 78 in your books. Okay, just a couple of pages ago when we did condensation polymerization. You do need to be able to draw these structures. Okay, so just very quickly, let's remind you. Meth means 1 carbon, eth means 2 carbons, prop means 3 carbons, bute means 4 carbons, okay? So, say for propanol here, prop tells us he's got 3 carbons in a chain, 1, 2, 3 carbons in a chain. Propan-1-ol tells us the functional group, okay? The functional group of the alcohol is ROH. The OH tells us that functional group there is on the first carbon. So you may be saying this is the 3rd carbon, 1, 2, 3, but of course, remember molecules move, they're moving around the whole time in solutions and gases. So if it moves around and turns itself over, then it's the same molecule. So it doesn't matter whether you draw the OH here or the OH here, it's still propan-1-ol. Likewise, butan-1-ol, bute. Okay, the functional group in 1-ol is on the 1st carbon or the 4th carbon because it's the same molecule. If the molecule turns over that way, it is the same. In the same way, likewise, you can have propan-2-ol where it would be on there. You can have butan-2-ol where it would be on there, but it could also be on there because if the molecule turns over, then it really makes no difference. Okay, functional group on alcohols, OH. Functional group on the carboxylic acids is it's carbon, double bond to oxygen, single bond oxygen, single bond hydrogen, much bigger functional group. The thing when drawing these is always count the bonds on this carbon here. Count the bonds, 1, 2, 3, 4. Most students make a mistake and put a hydrogen on it as well. That would make 5 bonds. So that carbon there, okay, other than in methanol, doesn't have a hydrogen. Look at it. Okay, be wary of that. The ending of the name is anoic acid. That tells us it's a carboxylic acid. So prop 3 carbons, anoic acid, a carboxylic acid. So that ending there is important, anoic. Likewise, the ending on alcohols is ol. Okay, so a bit more information now about the alcohol and carboxylic acid homologous series. First off, a quick recap. What are the alcohol and carboxylic acid functional groups? Well, we need an R there just to say a length of carbon chain. It could be C1, C2, C3, C4, depending on which molecule we're looking at. That's not important, the length of the carbon chain to the functional group. The functional group for the alcohol is the OH group. Okay, so that's the functional group. Carboxylic acids now, the carboxylic acid functional group has to have a carbon in it, double bonds to an oxygen, single bonds to an oxygen, and a hydrogen. There is our carboxylic acid functional group, and we can attach whatever we want now to that bond there, but this is the functional group of the carboxylic acids. Now you can make alcohol by fermenting glucose solutions. That's what we're going to do here, write a balanced symbol equation for that. So glucose is C6H12O6, glucose is sugar. And of course you get lots of glucose sugar in grapes, so you can ferment grape juice. So C6H12O6 solution, aqueous, if it's a solution. That's going to ferment and make ethanol, that particular type of alcohol. Now people in the real world call ethanol alcohol. But alcohol, of course, is a family of compounds. It's ethanol. It just happens to be one molecule, one member of that family. So ethanol, C2F, C2 carbons, H5, there's going to be 5 hydrogens surrounding those carbons, and there's going to be the functional group, the OH. Now you could write that C2H6O, it's just we write it like this, it tells the reader it's the alcohol functional group, functional group there. Right, and that's what's going to make carbon dioxide, CO2. It's going to be ethanol solution and carbon dioxide gas. This, of course, is exactly the same reaction that takes place when you make bread rise. You use a yeast catalyst. Yeast is an enzyme catalyst that goes on top of the arrow there. The bread rises because the carbon dioxide gas can't escape from the dough. Of course, there's a little bit of alcohol in raw bread dough until it's cooked, when of course it evaporates off, and it's very, very dilute anyway. The carbon dioxide makes the bread rise, but the ethanol makes alcoholic drinks. You need to leave wine ferment for a few weeks. Now we need to balance the equation. I always say start with the first element. You see carbon there. I'm not going to start with the carbon this time because of course it is in both the products, and that just makes it a little bit confusing. H12, hydrogens. Let's do hydrogens first. H12, 5, 6. There's 6 hydrogens here, there's 12 there, so we're going to need 2 of those molecules. Okay. Right, so now let's have a look at the carbons and go back to that, because oxygen appears in both of them as well. So carbon now. C6, well, I've got 2 times 2 is 4 there. That one makes 5. Well, let's put a 2 there to make 6. It might work this way. Let's give it a go. That's now 6 carbons. Right, now the oxygens. 6 oxygens there. 2 oxygens there. And 2 times 2 is 4 oxygens, there's 6. So that does actually work. So that works quite nicely. Okay, next to it says complete the equation below by drawing the structures of the molecules involved in the dehydration of propanol. Okay, dehydration, well, that's taking water out of propanol. So 1, 2, 3. Okay, propanol, OH. Okay, hydrogen, 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 hydrogen. So dehydration, so that's going to make water. Okay. Water's H2O. So we're going to have that hydrogen come off, that oxygen come off, and we're going to have another hydrogen come off. Okay, so that the other hydrogen is going to come off of this molecule here. So we're going to take a hydrogen and the oxygen hydrogen there. So let's draw that. Okay, but without the OH on the end there. Okay, so we'll imagine that hydrogen's there now. Okay, so we've taken the OH off. I'm going to take a hydrogen off this one as well. Okay. So this now doesn't look right because this has got 1, 2, 3 bonds. This has got 1, 2, 3 bonds. So we end up with a double bond in there. And this, of course, is propene. So you can dehydrate an alcohol, propanol, and what you get is the corresponding alkene. So you can do the same with butanol here. Okay. So 4 carbons in butanol. OH on the end. Okay, you can put the OH down there if you want to, because these the reality is this is a 3-dimensional structure, and so just writing it like this, we do it for ease of what it looks like. So if it were to help you, you could just picture the oxygen hydrogen coming off, and that hydrogen, you could put the oxygen hydrogen there. I've just done it a force of habit, I suppose. Okay, the point being, doesn't matter how you draw it, so long as you understand it. And what the dehydration takes the oxygen, hydrogen from here, and this hydrogen from here. Okay, and we end up with the corresponding alkene, like so. Okay, dehydrations of alcohols make alkenes. Don't be tempted to put the extra hydrogen on there because it's got 1 bond, 2 bonds, 3 bonds, 4 bonds. That's now right, plus H2O. 2 uses of alcohols, several uses of alcohols. Alcoholic drinks. Okay, it's probably the one that springs to mind. Maybe that says more about me. Alcoholic drinks, it's also used as a fuel. Often we're putting some ethanol and mixing it with petrol nowadays. You can grow sugar in fields and ferment it to make alcohol, so you can make biofuels. You make the petrol go a bit further by putting some ethanol in it. It can be used as a solvent. It can be used as methylated spirits in camping. So there's a couple of uses there. I don't think you need to know those too much for the exam. Next page. The apparatus for the fermentation of grape juice is very simple. We just need a big old demijohn. Oops, that's a rubbish story. Big old demijohn, big old jar. Okay, now in the top of it, okay, there is a trap, because this has to happen without oxygen. Okay, so the traps sometimes looks a bit like that, and what happens is you want the carbon dioxide to be able to get out. Okay, so this is our sugar solution, and yeast. You want the carbon dioxide to be able to get out, so you put water in here. Okay, so the carbon dioxide now pushes that down. It goes up there, and then this is a nice bigger bit here. So when the carbon dioxide pushes the water down, the carbon dioxide can escape, but the water stops any oxygen getting back in, because of course if oxygen gets back in, the alcohol can oxidize. Okay, so that's like a trap to stop the oxygen in the air getting in. Okay, to stop oxygen getting in. Oxygen from the air. From air. Okay. Name the technique, draw a diagram to explain how ethanol solution produced from fermentation can be turned to a much more concentrated solution. This is going to be fractional distillation. Okay, and we did it in year 10. So because ethanol and water have very similar boiling points, so about 75 for ethanol and about 100 for water. So simple distillation will not work. And you need to concentrate it because, of course, from this fermentation here, you only get solutions of about 12% alcohol, because as the alcohol is produced, it poisons the yeast catalyst. So you can't get any more concentrated than 12% ethanol there. So we need to concentrate it. We'd need fractional distillation. Fractional distillation needs a fractionating column. We'd often have a round bottom flask at the bottom here. And we have a long fractionating column. It allows the ethanol would evaporate first. So this is our ethanol and water. Ethanol boils about 75 degrees, say. Okay, water boils 100 degrees. So as you heat that, the ethanol is going to boil off first. But of course, water evaporates. When it rains, the bubbles evaporate, don't they? So the water evaporates as well. So this is why we have a long column up here, because it gives the water plenty of time to condense and turn back to a liquid, whereas the ethanol won't, because we're above the boiling point. We have a thermometer at the top here. And then here we have ourselves a condenser. Condenser is just a cold place. It's kept cold because it's got a jacket around the outside of cold water the whole time. So that's water in, cold water in, and then it comes out at the top there and goes down the sink. So this is a cold area, a condenser. Okay, and at the end of there, so the alcohol and water, the ethanol and water evaporate off. Okay, the water is not going to actually the water's boiling point. So the water somewhere up this fractionating column, will condense and drop back down. Okay, but the temperature is over 75 degrees, and we can read that on the thermometer there, 75 degrees. The ethanol won't condense because it's above the boiling point, so that continues to rise. Okay, goes past the thermometer, 75 degrees, so we know it's ethanol. Into the condenser, it's cold here, it's much cooler than 75 degrees, so it turns back to a liquid, and then out of here we get our drops of pure ethanol. Okay, when the ethanol's all gone, then the boiling point the temperature will rise up because the ethanol's gone. So the boiling point, we then get to 100, the boiling point of water. As soon as we see the thermometer starting to rise, we know we have to change this beaker. Okay, and that's how we get ethanol. Okay, so that was that page. Let's quickly get onto the carboxylic acid. So I'm running a bit short on time. What's the functional group of the carboxylic acid? Well, we say it's C, double bond to the oxygen, hydrogen. There we go. If wine is left open to air, what does the ethanol turn into? It turns into the corresponding acid. You may have heard your parents saying, if they drink a bit of wine, okay, and it's been left open on the side, that's turned to vinegar. Because wine will oxidize, okay, and make a carboxylic acid. So ethanol will oxidize into ethanoic acid. Ethanoic acid is vinegar, okay, so that's what happens. You can oxidize alcohols and they turn to the corresponding carboxylic acid. Is that oxidation or reduction is our next question. Oxidation. Okay, what effect would a carboxylic acid have on litmus paper? Well, it would turn it red because it's an acid. Carboxylic acid litmus paper turns red. Okay, so we did reactions of acids in year 10. Acid plus metal oxide. Okay, the hydrochloric acid and iron oxide makes iron chloride. So that's just straightforward revision of year 10 with a common lab acid, hydrochloric acid. Metal oxide, acid plus metal oxide makes water. Okay, likewise here, acid plus metal hydroxide, salt plus water. That's with the common lab acids, but we can do this with carboxylic acids as well, and that's what we have down here. Exactly the same things, just with carboxylic acids. Now, the only thing you need to know is ethanoic acid makes an ethanoate. So copper ethanoate. So it's exactly the same chemistry as year 10, but we're using a carboxylic acid and the ending is ethanoate instead of, say, chloride or in this case nitrate, or in that case sulfate. So copper ethanoate plus water. Okay, ethanoic acid plus magnesium carbonate. That's going to be magnesium ethanoate. Okay, it's a carbonate now, so that will be plus carbon dioxide plus water. Okay, propanoic acid, mate, is going to make propanoate, calcium hydroxide, calcium propanoate. So the ending is anoate for these neutralization reactions, plus carbon dioxide plus water.